Hello, good morning. I hope everyone is doing well today. So on Monday, we talked about rotational kinematics, right? We went over the equations we're going to use for rotation if it has a constant rotational acceleration. So here we have one more example problem we're going to solve. Okay, so let's take a moment and take a look at this question, okay? All right, so we have two wheels. One of the smaller, one is bigger. So they're connected by a belt. So we have looked at this before. If they're connected by a belt, which means they have the same, some kind of velocity. What kind of velocity do they share in common?
Linear velocity?
Linear velocity, very good. So if wheel A will have the same linear velocity as wheel C, sorry, B is the belt. They have different radius, okay? And also tell you wheel A increase the angular speed from rest at this rate. So this is really just telling you what the angular acceleration is. Right? This is alpha A. Okay, so now the question is, we want to find the time for wheel C to reach this rotational speed. So we need to find the angular acceleration for wheel C. So let's solve this one together, okay? Given that wheel A and wheel C have the same linear speed, and a linear velocity can be written using the angular velocity by multiply with the radius r. So r times L omega is RC times omega C. Excuse me. So they both, radius is given, so we can use that radius here. That's 10 centimeters. And the angular, I'm sorry. This is given the angular acceleration. Okay, so we can't really use it directly quite yet, but let's modify this just a little bit before we can use it. If we take the derivative with respect to time, okay, on both sides, R is a constant, the omega dt is simply R alpha. Okay. So this is alpha A, and this is alpha C. So their angular speed is related proportional, inversely proportional actually to their radius, and so is their angular acceleration. Okay, now we can plug in numbers in here. 10 centimeters, this is 1.6 radians per second square. And this is 25 centimeters, and we want to know alpha C. So from this equation, we can find the angular acceleration for the bigger wheel is 0.64 radians per second. So it's not going to be as big as the smaller. The smaller has to speed up so much more faster to catch up and keep up with the bigger wheel, right? Okay, so we found alpha C. Now we want to know how much time it takes to reach the speed. Now the speed is giving us 100 revolutions per minute. So do you think they have given us a linear speed or angular speed? We can convert this directly to an angular velocity, or is this a linear velocity? What do you think?
It's an angular velocity.
Thank you. Very good. Okay, so 100 revolutions per minute. How do I change that to omega? How do I write this in the unit of radians per second? What do I do?
Well, what we could do is convert from minutes to seconds.
Okay.
So quick maths. So that's 60 seconds in 1 minute. So we could just multiply the top by, oh yeah, we could do it that way too. Do you want to keep 60 seconds on the bottom?
Well, eventually we cancel, right?
Okay.
Yeah.
So for now, we're going to do it that way. Okay. And then, yeah, someone in chat also said the 2 pi equals 1 revolution. So we could just, substitute for that also.
Thank you so much, Juan, and thank you, Jacob and Miko for Elena for contributing. So 2 pi, this is radian, and we can get the angular speed, 10.47 radians per second. Okay, so we want to start from rest to this speed. I want to see how much time it takes. It's speeding up at a steady rate. So let's take a look at our equations. We said we can use the same equations as before, right? So here we're going to use this equation because we're given speed, we're given alpha, we want to find time. So we're going to use that equation. Let's say alpha, omega c final is omega initial plus alpha times how much time it takes. It start from rest, it speed up to this speed, and our alpha has just been calculated. And we want to know what is the time. So time is simply 10.47 divided by 0.64, and you get the units, you get seconds. So that's correct. So our T is 10.47 over 0.64 seconds, and 16, roughly 16 seconds. Okay, so that's just a quick example showing how the equations we derive can still be used here. That's what we're going to do for kinematics. In translational motion, what do we do after kinematics? We look at the forces. We are relating force to acceleration. Force is causing a change in the motion, right? So just like that, here we're going to look at the rotational dynamics where the torque is causing a change in rotation. So we're going to find the counterpart of force in rotation, which is now torque. So what we're trying to do is, as we did this in the lab, F equals ma, that's Newton's second law for rotation, for a translational motion. For rotation, force become torque, and A become alpha, and mass become I, the rotational inertia. So we're going to look at these terms one by one. We already looked at alpha, right, in the kinematics. Now we're going to look at torque and how to calculate torque. And eventually we want to look at rotational inertia and how to calculate I. After that, we're going to put everything together to do some problems using Newton's second law for rotation. So let's start with torque. Torque basically, just like how force causes a linear acceleration, your torque causes angular acceleration. Not only it depends on how big of a force you apply, it also depends on where you apply the force. So for example, you can apply a force here that's going to generate a large torque. If you hold your wrench real close, you give yourself a much smaller level arm, and you're gonna have to generate a smaller torque. So both the distance matters, both the amount of force you apply matters. Also, the direction that you apply the force matters, right? You can apply it perpendicular to the distance. That's going to maximize the amount of torque you generate. But if you apply it in the same direction as your radius r, distance r, you're not going to generate any torque because you're simply pushing in and it's not going to start rotating. So we realize, okay, it looks like when they are at 90 degrees, right? When they're at 90 degrees, we have the max amount of torque. So if we factor that angle in, we can write torque using r times f times sine of the angle. So if the angle is 90, it's going to be 1. If the angle is 0, you get 0 torque, which makes sense. If your r is here and your force is also here, sine of 0 is 0, or sine of 180 degrees is 0. It turned out this can be also written using a cross product. Okay, so this will be the official definition for torque is R cross F. We're gonna look at a little bit later on how to do a cross product, but first let's take a look at the demo.
This is a demonstration of the lever arm and the importance of the lever arm in determining the torque. A torque is a turning force.
Professor, I don't know if you meant to pause it. I mean, take out the volume, but we can't hear it.
Okay, I'm sorry, what?
We can't, I don't know if you meant to, but we can't hear the video.
Oh. Okay.
I think it's when you mute yourself that it does that.
Oh, I see. Oops. Oh.
Wood to my able assistant Parker, who will grip the wood with his hands. Then I have some hooks here to which I will attach this mass at different locations. So the torque exerted when I attach the mass here will be less than the torque exerted when I attach the mass, say, here. The axis of rotation is here. Parker will be attempting to prevent this T from going down. And as I attach the mass at farther and farther points from the axis of rotation, the torque will increase because the lever arm is increasing. So let's have a try here. See how tough Parker really is. No problem. A lever arm of maybe 20 centimeters. Again, not bad. Not bad at all. And he's starting to strain. That's the best I've ever seen anybody do it. So give a hand to Parker and
All right. So in that video, they demonstrated the lever arm, the distance R and F all made a difference in terms of how much torque it generated. If we had the demo ourselves, we will also use, if we could do it ourselves, we will also use different weights. Even at the same lever arm, you can always change the F and you're going to increase the torque as well. Torque here is a vector. Okay, so you can see that we say the units for the torque is Newton times meter, which is the same unit for work. Remember, work has a unit of Newton times meter. But in that case, we say you can also use joules to represent it. But for torque, we're going to keep it as Newton times meter. We're not going to change it to joules. Why is that? Because it's not the same as energy. It's a vector. Energy and work, those are also all scalars. So just keep it as Newton times meter. To calculate torque, the official definition is R cross F. Okay, so what is R vector? R vector is from the center, from the axis rotation to where the force is being applied. So let's go back to the torque bar demo. Here I'm showing a distance R, and R vector is from, this is your rotation, this is where your force is being applied. So draw a vector arrow from here to here. That is your R. In this case, this is my F, right? If you put your force here, then drawing an arrow from here to here, that is your R. Okay, so that's how R is defined. It's a cross product between R and F. Maybe some of you have already seen how to do a cross product, right, between two vectors. The magnitude of the new vector C is A times B times the angle between A and B. The direction of C is perpendicular to both A and both B. So A and B can form a plane, and C is going to be perpendicular to the plane. We can also figure out the direction using right-hand rule. Okay, so you probably have done this already. We can do right-hand rule in two different ways. I'm personally like to use method 1 more, but some people like the other method. So we're going to do the right-hand rule together. Okay, method 1 for doing a right-hand rule is you align your forefingers with the first vector. So in this case, my A is given, and I'm going to curl my finger toward the second vector. So you can see the second vector exactly where it is, doesn't really matter. They're going to give you the same direction for C. So my B is toward me, right? It's toward you. So you're gonna curl your finger towards yourself, and the thumb give you the direction of C upward. So that's the first method. Now, if your B is away from you, you can see if your B were here, you align your forefingers and you're going to curl it toward B. In this case, B is away from me. I have to flip my hand, and consequently, my C will be downward. That's the first method. Let's do the second method. Second method, forming an XYZ axis using your use your hand. So you can either do this, so one axis, another axis, and the third axis, okay, or you just use one of the fingers. So in this case, use your index finger and let it point in the direction of your first vector you're trying to do a cross product on. And your the middle finger, or the rest of the finger, whichever you prefer, will be pointing in the direction of your second vector. And your thumb will give you the cross product direction, which is C. So they both will give you the same results, of course. So which way you like to do it, this way or this way, it's up to you. We'll get to practice using it later in some of the questions we see. There's some rules for cross product. You can see if I use A cross B, or if I flip it to B cross A, the final result will be in the opposite direction. You flip the sign, right? Which makes sense if you were looking at this one. If I do B cross A, I should have done like this. Right? It will flip the direction for me. If A and B are perpendicular, the cross product, the magnitude of this becomes simply the magnitude of A times B. So this is a generic torque. You see formula is F times R when they are perpendicular. Okay, when they are not perpendicular, you have an angle. Like when they're 100% parallel to each other, the cross product becomes 0. This is when you generate no torque. If your R and F are in the same direction, you're going to get no torque. Okay, let's do a really quick check on our understanding how to do a cross product. Let's see the first question, this one here. So here in XYZ Cartesian axes coordinates, your X is also directed. You can be denoted using I hat, the direction. Y, sometimes people write J hat. The Z direction, people write K hat. So what is J hat cross I hat plus K hat? Okay, so I will let you vote on this. It should be quick, so I'm not going to give you any time to the discussion in the breakout rooms. All right, 10 more seconds.
Professor,
Yes,
can I quickly take a look at 2 previous slides above, please? I forgot to write something down. So 2 more, I believe, where it's like the torque is also a vector.
oh, this one.
Yeah. Okay, thank you. I got it.
All right. All right, seems like I've gathered most of the votes. I'm going to go ahead and end this. Okay, so this is our results. Okay, so here we need to do a cross product. Which method did you use?
I used the hand rule.
Right hand rule. You used curling one or just the 3 fingers one?
Yeah, method 1, the curling hand.
Method 1, okay. All right. And let's do it together. So what I'm trying to do a cross product between J and I, J cross I. J is my first vector. So I need to align my 4 fingers with the direction of J, pointing to the right. Okay, pointing to the right. And I need to curl it toward myself. I realize I can't do it to myself because my X is here. So I need to flip my hand and point it to the right this way so that I can curl it around toward the second vector, which is I hat, which is toward myself. So my thumb is pointing downward. So J hat cross I hat gives you what?
Negative K.
Negative K hat, very good, downward. Negative K hat plus K hat gives me 0. Okay, now if you use the second method, okay, Y is to the right. Okay, my first, I don't know if you can see. Index finger pointing to the right and X toward myself. I don't know, you cannot see, and thumb points down. So it's negative K hat, okay? In terms of doing a cross product between the basics of the your coordinates, there is more of a sort of a fast way, so you don't always have to do it. You can just memorize it. Is IJK, if you write it in order, IJK from left to right, or you can say XYZ, doesn't matter. Okay, so if they're doing cross product in order, I cross J gives you K, so always in order. J cross K give you the next one is I. Okay, and K cross I, again from left to right, K cross I give you J. So that way you don't have to always do a right hand rule, you can just memorize it. But if it were reversed, it's not I cross J, but J cross I in a different order, that's going to give you a negative K, right? If it's I, if it's not K cross I, it's I cross K, that's going to give you negative J. Okay, does that make sense? I cross J give you K, J cross K give you I, and K cross I give you J. So that has to be in the IJK order. Okay. So that way, maybe it's easier, quicker to figure out the answer. The same applies if you have a cylindrical coordinates, is S hat, phi hat, and Z hat. It's the same way. S cross phi give you Z, phi cross Z give you S, and Z cross S gives you phi. If you do cylindrical, R hat, theta hat, phi hat, again, write them in order, you can always figure out the cross product. But we are not gonna run across these in 1510, so you don't have to worry about it. Okay, so that's a really quick check. Let's look at a bridge question you have already done to calculate torque. Here we are presented with two different cases. They are provided with the same force, but the force where the force is applied is different, and the angle in which the force is applied is different. So we want to compare the torque in the two different situations. Case one, force is perpendicular to my R. So let's label the R for both of the cases. From the axis of rotation to where the force is applied. So this vector is actually, this vector is my R. And they have a 90-degree angle. So the torque in this case is simply F times the magnitude of R times sine theta, sine 90 degrees. So sine 90 is 1. So it's just FL over 2. Case 2, force is applied here, and this is applied here. My R is, again, from the center of rotation to where the force is. So this longer vector is my R. To calculate torque, you do R times F times sine theta. Here the angle is 30 degrees. Okay, what is R? R is now L. F is still F. Sine of 30 is 1/2. So you can see that it's the same torque generated in both cases. Okay, so they're the same. Any questions about this one?
I think I might have missed it, but in this case, you know how mass would equal inertia? So then in this case, the inertia would be the sine of the degree. I'm a little confused on that part.
We are not doing the inertia part yet.
Okay.
So, okay, torque is equal to I alpha. So this is a rotational inertia you're
Right.
referring to. We are simply now looking at torque by itself. And after we do that, we're gonna look at rotational inertia, but that's coming up later, okay? Yeah, so right now, don't worry about the I, because we're not doing the Newton's second law yet. We're just looking at torque by itself. Okay, so let's look at this question. To figure out the direction of torque, there's also a quicker way. Instead of doing R cross F, you can simply look at in what direction that it's going to cause this to rotate. Okay, we had talked about this in the lab, said a counterclockwise rotation is what we consider to be a positive torque. A clockwise rotation is what we consider to be a negative torque. So you can see that here you have a wheel, and the plane of the wheel is an XY plane. This is my X and Y. So I didn't draw my Z, but which direction is my Z? My Z is pointing out of the page, pointing toward you. So this is my Z. I put a little dot on it. The dot means pointing toward me. Like if you look at an arrow, if you look at from the tip, you only see a dot, right? So that means coming towards you. That's the Z direction. So which one of these forces produce a torque that points in the positive Z direction? So we know that in our convention, a Z direction of rotation is corresponding to a counterclockwise rotation. Okay, if it's in a negative Z direction, it is it's corresponding to a clockwise rotation. So a quicker way to figure out the direction of the torque is simply to see which direction they're pushing the wheel. Do you think they're pushing it to attempting to generate a clockwise rotation or counterclockwise rotation? Okay, so with that in mind, let's try to answer this question. So this one, you may do a really quick thing. Look at the direction. You say, okay, I know which force it is. I also want to ask you to try to cross-reference that with the R cross F, which is a more difficult method to see, does that give me the same direction? Okay, so take a screenshot of this page, and we are going to do a brief discussion in the breakout rooms. I will be visiting room 4, I believe, because I was done with room 3 last time, today.
Oh, hi.
Hello,
Hi.
how's everyone today?
Good, and you?
I'm doing well. Getting over a cold, so
Oh,
but
are you
it's
feeling better?
yeah, I am better.
That's good.
Thank you. I think I shared my screen. Let me try. I don't think you can see my screen, right?
I see. Welcome to your new iPad.
Okay, that's still that old page. Let me. It should come up with my slides.
And I see right now you're on iTunes, and then there's there behind iTunes there's Safari.
Oh, I'm sharing my desktop. That's why. Okay. Very good. I wonder. Okay, so what do you think? Julian, Lee, and Mark and Mark. You can also chat. Just type in the chat if you could not use your microphone. Which one of these forces produce a torque that points in the positive z direction? So if we say positive z give you a counterclockwise rotation, so which one of the forces can push the wheel to rotate counterclockwise?
Well, I think F4 is ruled out because that one produces clockwise rotation.
Okay,
Oh, something in the chat. Yeah, I agree with Julian about F2 because it's kind of pushing it towards like upwards
mhm.
at its current position, and that would produce counterclockwise.
Yes, very good, thank you.
F3, I don't think it would have any torque, so no rotation.
Mhm. F3 is pushing toward the center, is not going
Yeah,
to rotate.
and neither would F1, I think.
Yes, very good. Excellent. So simply by looking at which way it rotates, you can see this is a much quicker way to decide the direction of the torque. Excellent. So F2 is the correct answer. What if we were to check it with R cross F? So let's draw the R here. R is from the center of the rotation to where the force is being applied. Now, if we use F4 as an example, this is my R. Okay. So we need to do R cross F. Notice now they're in the kind of in this direction. So we can always move our vectors in the parallel way so that is easier to look at. So in this case, you can move your F downward a little bit, saying, okay, F4 is downward. So it's in this direction. So I can extend it, or also I can move it sort of parallelly downward. So my F4, I can write it, I can move it here. I know it's not at the center. I'm simply moving it in that way, so it's easy to do a right hand rule. Okay, so R and F. So if I try to do a right hand rule here, my R is this way, my F is over there, so I curling toward F, which makes sense, that's that direction, and give me a downward, which is actually pointing into the page, downward, is negative z, right? F4 give you a negative z. So you can see that still gives me the same result as if I were simply looking at which way it rotates. This is just faster. Doing the cross product is a little bit slower. Okay, all right. Does that make sense? Any questions?
Yeah, that makes sense.
Yeah, it makes sense.
All right. Well, thank you all for contributing. I will see you briefly when we return. Okay, 10 more seconds. Let's take a look at this together. Okay, all right, let me go ahead and end this. All right. Okay, so there are 4 forces here. Can we figure out some of the forces does not generate any torque, right? So which one of these forces don't generate any torque? And then if it doesn't generate any torque, we don't even have to consider. So it's F1 pointing toward the center and F3, thank you very much, Jacob. They're going through the center is not going to be able to push the wheel. Okay, so F4 and 2 will be able to push it, the wheel. And as you guys voted, majority you said 2 will give you a positive Z direction. Let's see, to put 2 is this way, so we're going to kind of push it in this direction. So that's clockwise, sorry, counterclockwise, positive Z, very good. And 4 is going to push it going this way, right? And that's clockwise, negative Z. Very good, so B is correct. If we were to do a right-hand rule, let's do right-hand rule together. So one of the forces, for example, let's do F2. Where is R? R is from the center to where the force is being applied. So this is your R. R cross F. So to do an R cross F, you want to be able to kind of align your vector, so it's easy to, you can move your vector so there are tips, their tails aligned, so it's easy to do a crossbar. So I can move R up and down, or I can move my forces up and down. If I move my R downward parallelly, okay, so I'm going to move it here. So this is my same R. So you can see now this is A cross B. Let's do the crossbar together. Your 4 fingers pointing toward R, your F is here, so I'm curling toward F. Thumb up, give me positive Z, right? Let's give me the direction of the torque, just consistent with simply just look at which way it rotates. Okay.
Can you do the cross product for F4 as well, like with the right hand rule? I don't know, I was having, that one was harder for me to do.
Okay, so right hand rule, let's draw the R. R is from here to here. And this is my F. And again, I can move my F, I can move R. Let's say we move my R. So I want it to be aligned with the F, their tail touch each other. So I'm gonna extend my R up, move it up, and move it to the left. So move it parallelly, right? So I haven't changed anything, I simply moved it. So R cross F, R is here, F is over there. So downward, right? Downward.
Thanks.
Okay. But just look at which way it rotates is much simpler. One last question before we end today. Let's look at this question, okay? So we have a uniform disk, the mass is given, the radius is given. It's in the XY plane. There are different forces acting on the disk, and you want to see the torque generated. Okay, so F1 is a force this much, 337 newtons at the edge of the disk on the positive axis. So here, okay, so we want to calculate the magnitude of the torque generated by F1. So how do we do that? We're going to say, okay, first question, torque generated by F1 is going to be R plus F, R1 plus F1. And in this case, R and F are perpendicular. So this, in terms of the magnitude, right, simply becomes magnitude of R from here to here That is my R, and that's just simply my radius. Radius times F1. Sine of 90 degrees is 1. So I'm not going to write that. It's sine of 90 degrees. No, that's just going to be your radius times your force. And you can find the answer for Newton meters. Okay. Also, this is a magnitude. If you need to tell people also the direction, you can see F1 is trying to generate a rotation in the counterclockwise direction, right? So it's going to give you a positive Z direction. So if you need the direction of torque, a more complete answer will be 45 meter in the Z direction. So it's in that direction. Okay, but for magnitude, you just need the number. Second one is, what is the magnitude due to F2? F2 is right here. So you can right away see that's not going to give you any torque because you're pushing toward the center, right? It's not going to generate any rotation. Or you can see R and F are in the same direction. Sine of the angle 0 degrees is 0. So this is 0 for F2. The third one, this one will take a little bit more effort to calculate. F3 is right here. Okay. All right. So if we again follow our definition, where is my R? From the center rotation to where the force is being applied here, touching the wheels right here. So this is actually my R3, right? Okay, R3 and F3 have an angle. This is their angle. That angle can be calculated. So a force acts on the edge of the disk at an angle theta 36 above the x-axis. So I shouldn't call this theta because this is the angle above the x-axis. So it looks like they're telling us this is the angle 36 degrees. Okay, so if that's 36 degrees, the angle between R and F would actually be 90 degrees minus 36 degrees, that's 54. Okay, so this is not, it's just 36 degrees. So to calculate the third one, torque generated by 3 is R3, F3, sine of the angle between them. R3 again is the radius, right? So it's radius times F3 of sine 54 degrees. So you can plug in the numbers of R and F3, you can get that answer. And in terms of the direction, it's generating a clockwise rotation. So that's going to be negative Z direction. Okay, so the torque 3 is negative Z direction. Okay, so that's a complete answer. But if you just want the magnitude, that's just 368 in the negative Z direction. So that's how you can look at the diagram and figure out where is your R, where is your F, and what is the angle between them. So when they're not 0 degrees or 90 degrees, that's less trivial. That is where you need to slow down and be careful to figure out the angle. So for example, right now, for this question, if you had used sine of 36, the angle, whatever angle they're giving to you, then that would be wrong, right? Because that's not the angle between your force and your level R. You want the angle between R and F. To interpret that sine theta, people can interpret differently. You can interpret it to be, okay, what is, so R is here, but the level arm is really just the distance that's perpendicular to your force. So you can think about, okay, this is my r sine theta. Sine of this angle is this level arm. Okay, so you can group this sine theta with your r to see what is the distance that is perpendicular to my force. Or alternatively, you can group the sine theta with your force to see what is the perpendicular force component to my vector r. So that's just a different way to look at it. If that helps you to do the calculation, feel free to do that. Otherwise, you can always rely on the definition just to find the angle between them. Right? Okay, so that's all we're going to do today. On Friday's class, we will talk about rotational inertia, and then we will group everything together with force and I and alpha. We can look at Newton's second law. Okay, that's all for today. I will see you on Friday. Have a good rest of your week.
Hi, Professor. Have a good day.
Thank you.
Feel
Bye,
better.
everyone.
Professor,
Yes.
sorry. I'm kind of confused on why for the magnitude of F2 would be 0.
The magnitude of the torque. So you can look at F2. Do you think just by looking at it, like if you push it in like that, do you think it's going to make the wheel rotate?
Oh, I see.
Yeah.
No.
And then also you can use the definition to see R and F are, R is here, F is here. The angle, they're in the same line. So the angle sine of, well, actually, in this case, is sine 180 degrees is 0, okay?
Right.
Yeah, so if you plug in the sine theta, you still get 0.
Okay, I see. And
Okay.
then, would you mind going back a slide? I had another question.
Here, this one.
Yeah. So I'm still kind of confused. So I know that the z-axis, that one goes into the counterclockwise direction, correct?
Mhm.
But in terms of like kind of depicting it, does it matter like where we place it, or does it have to be like, if that makes sense, like does it matter if we put it between y and x, or like, I don't know if that makes sense, but like,
To put the
does it matter?
z-axis, you mean?
Yeah, as long as it's in the counterclockwise direction.
Oh yeah, you know, it doesn't really matter you put it, right? It's pointing upward. So, right, it doesn't, like X and Y, what do you mean by where you put it?
So for instance, you know how our y-axis it's vertical and our x-axis is horizontal.
Mhm.
Like, does it matter if we put it, if our z is between the y and the x-axis? Like as if we drew it as a vector between those two
Oh
axes.
yeah, it doesn't matter. You can just kind of put a Z, just say upward,
Okay, so then
right? You
as
can
long as it's
write it
just,
anywhere. So as long as you're showing that it's upward. Yeah, is it directions? Doesn't really matter where you put it. It's sometimes, okay, like if we had draw a perspective view, usually we drew our XYZ like that, right?
right,
It's just for sake of drawing, you always like start your drawing from the same point, but it's just a direction. You might as well draw X here, draw your Y here, draw your Z there. That's still correct. It's not pretty to look at, but that's still correct.
okay.
Yeah, so it doesn't matter where you draw it.
Okay, so then, for instance, in this case, the y-axis would be, for instance, we could draw it, let's say where you have point F4, and
Mhm.
then you can draw it upward, and then you can draw your x-axis as if you were pointing from the endpoint of f of 2, and then you can just draw your z-axis in between, correct?
Like if I can draw my Y here, right? I can draw my
Right.
X here. I can draw my Z here, right?
Right.
Yeah.
Yeah.
Absolutely. You can move your axes wherever you want. Yes.
Okay.
Yes. Mhm.
Thank you.
Sure. Okay. Bye-bye.
Have a good day.
Thank you. Have a good day.